So in this video we start with covariance and introduce the concept of correlation matrix, and then introduce the concept, or let's say we just touch upon the introduction of principal component analysis. To begin with, we start with the definition of covariance. Covariance is basically how much two quantities change together. Okay, so M, let's say, is a data matrix of size n cross m, where n is the number of rows and m is number of columns. And from the perspective of data matrix, n represents the number of observations or samples, where m represents features in each sample. Then C, let's say we define the correlation matrix C as 1 over n minus 1 times m transpose m. We see that in some sense we are multiplying the matrix with itself, essentially with its transpose. So we'll get to see why do we do that later. So what we get is C, an m cross m matrix, square matrix, where Cij, the Cij is element ith element in the ith row and jth column, that Cij. That element represents the covariance between the features I and j. Now if we go to an example, let's consider the data matrix where the rows are given by samples and the columns are given by features. Here there are two features and three samples. The first feature is height and the second feature be weight. Height in maybe let's say centimeter or something, and weight is in kg or something. Then if we center the data, firstly we do centering of the data, and that is done by firstly calculating the mean and subtracting it from the actual data simply. So we calculate the mean for each feature, that is each column, and subtract it from the elements, or let's say subtract it from the columns, respective columns, to get the following matrix M, that is being showed. This is after subtracting the mean of the respective feature. And now we go on to see what is the correlation matrix C. C is defined again as 1 over n minus 1 times m transpose m, where small n is number of features, or it is m cross n, right? So if we are dealing with, so correlation matrix basically is in some sense we relate to covariance. So then n should be the sample number. So n should be sample number, I think. Yeah, n should be sample number. So 1 over n minus 1 is used for sample case, because we use total n in the case of population. So n is, yeah, number of samples, n is samples. So we substitute it just, and we end up with this C as 20.333, 22.8193, 22.8193 and 26.333. Now we move on to interpretation of C matrix. Firstly, in case of diagonal elements, Cij. So diagonal elements are the elements where I equals j. So those are the elements which are along the diagonal. Cii gives the variation of height, and C11 gives the variation of height, and C22 gives the variation of weight, basically with themselves. C11 is variation of height with itself, and C22 is variation of weight with itself. Then just to experiment with this, just to play around, what I've done is we take W max minus W min and H max minus H min. We get the values 10 and 9 for them respectively. then we see C22 is greater than C11. C22 is weight, right? C22 is weight, and C22 is variation of weight with itself, and C11 is variation of height with itself. Then we see C22 is more than C11. Then that says that weight has more spread nature than the height. So this is one interpretation. Now coming to off diagonal elements, or let's say spread nature, I also mean variance, the variance spread, that basically relates to the spread nature. So off diagonal elements are again referring to the matrix 22.8193 and 22.8193, same both. So the value 22.8193, approximately 22.82, indicates that there exists a positive correlation between height and weight, because the element is basically positive. 22.82 is positive, so there is a positive correlation. That means that if one increases, other also increases proportionally, and how proportionally, that's a different thing, that depends on the magnitude of correlation. But for now, let's stick with this, that it is positive, and if height increases, it shows a relative increase in weight based on the data. So the height, the higher Cij, the more strongly are the ith and jth features correlated, of course, just as I have said. Now to summarize this, the covariance matrix provides valuable information about the relationship of each feature with itself, that is the diagonal elements, and with other features and the off diagonal elements. While this matrix explains the relationship between features, we cannot infer about the dominant direction of the data spread directly. If we plot the actual data, we cannot directly infer that in which direction is the data dominantly spreading by just referring to the correlation matrix. That thing we cannot infer from the correlation matrix. So that is what mentioned here. This is where the eigenvectors step in. The eigenvectors gives the most significant directions of the data spread or the axis of high variance. The first eigenvector giving the highest variance, and actually it can be arranged in descending order, so we'll deal with that later. So yeah, now we step into the domain of principal component analysis by introducing the concept of dimensionality reduction. By finding the direction that captures the most variance in the data, the dimensionality or the number of features, because each feature is treated as an independent dimension, because the features, as long as the features are not dependent on each other, that is to say each feature is independent of all other features, we can treat each feature as each dimension. So the dimensionality or number of features can be reduced by considering the eigenvectors corresponding to the largest eigenvalues. So this is for the introduction. Here on, in the next video, we will do an example and we'll breeze through it quickly.